Okay, welcome to week 7. Today we are going to do the physical layer. And if you see from the bottom, that's layer 1 from the bottom. So up till now, after this session, you are able to then do your midterm test. Because in your midterm test, week 1 to week 7 is covered. So just to have a quick recap, how many different layers we have? Name it.
Network layer,
Network layer,
data link layer,
data link, anything else? See, this is how it happens. Like for you people, it's important. For example, we have a gap of
yeah,
3 weeks, and it means that it is not only for this subject; it's for every subject. So if you're not revising your things, it would be really hard for you to remember it. So there is one important thing which I actually explained to the other classes as well, which you need to put it in your mind. For example, if you are going to when doing a driving first time in your life, how difficult it was. So you're scared, you're puzzled, you're sweating, you're confused, and so many thoughts are coming at the same time in your mind. Because why we are so much feel scared? Because we know that I don't have any chance of any mistake. If there is a mistake, there is a huge penalty, or maybe I have to pay for it, or for the damages or something. Similarly, if we take this thing to the other stuff as well in our life, then maybe it makes more sense to you. So what happens is that when you eventually do that driving again and again, and the time comes maybe 5 to 6 months later on, you even don't realize that you are driving and you are doing 5, 10 different things at the same time. Your different body postures, your leg is moving by itself automatically. Why it is happening? When you do a practice, some of the knowledge which needs to go into your subconsciousness, then that becomes a skill. Skill is not like that thing. For example, you attend a lecture today, or maybe you have done your degree but you haven't practiced, or you are not actually repeating those stuff or not doing the practice again and again, then that thing is not going to in your subconscious. If it's not in your subconscious, it means that you are not a skilled person. Like the way how if you are not driving, when you start learning driving, and in very few days in the start you left it, you can't then drive like the way how you want to be. So this is the same thing for you to understand, that when you are learning your courses, it's important to revise again and again. The point comes that is part of your subconscious. Once that is part of your subconscious, then it is more like a skill set, because you don't need to remember it now. For example, if you learn cycle in the childhood, you know how to ride. Okay. So similarly in education as well, in any subject when you are learning, whatsoever the knowledge you are getting in, the important thing is do it as much as many times that it's part of your subconscious, like where your subconscious is actually giving the signal to your body to do that task, and you don't need to memorate that thing. That makes a difference in your learning. So please, so you can see this is as example for you. So if you are not touch with your studies for 3 weeks, how it would be then? So in the layers, if we see that there is an application layer, then we have a transport, network layer, data link, and then this physical layer. So we already have done application, transport, network, and data link, and today we are going to do physical layer. So important thing to understand is that for every layer there is some important points which I explained you several times. For example, for data link layer, we know that it's all about MAC address and network interface card. Okay, in the NIC card, which I said. For the network layer is more like the IP addresses. Transport is about the TCP, UDP, or port numbers, which we done last time and in our last week, which is about this transport layer where we have done about segmentation, reassembly, port numbers. Any port numbers things are done on this layer. Transport layer is actually looking toward two main things: TCP and UDP. And in the TCP, we always do a three-way handshake, and that's a job of on transport layer and flow control. So in today's week, we are actually looking toward physical layer, which is now the first layer from the bottom. And in this layer, it is a physical connection between computer with other devices on the network, either with the switch or with the routers. So that's the physical wire we are talking about. Okay, and in this week we will investigate what are the analog and digital data, what is the data flow, what is the multiplexing, Manchester coding, how it is done in the Ethernet, transmission media, what are the different transmission media. So these are some of the important points which we'll do today in week 7. So starting from first of all with the types of data. So there are two types of data: digital and analog. From your everyday life example, what do you think? Any example in your mind about analog data or digital data?
Digital means like today's generation. Digital.
Sorry, which one?
Today's generation. The all the
No, no, I'm just giving you, asking you a very simple example of our life, where our data is in analog, where is our data in digital?
Email.
Email? How?
How like we can say that through internet
Yeah.
and like with
No, no, I'm not talking about that thing. I'm talking about analog signals, like any practical examples, like what is the difference between analog and digital. This is in terms of computers. When that data is sent over the wires, it is in the form of in the wires, it is in the form of digitals going on in the transmission media, but our voice is analog.
analog. Yeah.
Why? Any examples of from the our practical life? We know there is a analog clock, a digital. This is an analog clock which is in front of you.
and the digital display.
What is a digital clock?
Displaying the number.
Number. So what is the difference?
Well, we can see
What is the difference? Like if this is analog clock and digital clock is exactly have a number, like for example, on your this one is a like a analog type of thing 204. So what the difference you will find it out? Any idea? One other thing is in the analog, in the digital, we are either in 0 or 1. So see, okay. For example, you are going to buy a product, or you want to do a, you are going to buy a gold, 2000 gram. What do you want? Do you want to do the scaling on analog one or digital one? Why?
more reliable.
Why reliable or something else? More?
Trustworthy.
Why we need digital then? Why I can do the analog as well?
It's more accurate.
Accurate, accurate. That's a actual word I want to take it from your mouth. Okay, accurate. So that's a difference. Analog, we are not sure what exact value is. Maybe if I am buying something for $10, I can say okay, that's fine, and do it at analog. But if I'm actually doing something more precious item or very expensive, I will go for more like a digital scale. So thermometers are digital as well. They have in analog as well. So if we see 0 and 1 is in the digital. So but if I say that how many number of values can be possible between 0 and 1? How many? Why? Do you agree with him? Is there infinite values between 0 and 1? What do you think? Okay, his answer is there. What do you think? Yes or no?
Yes.
Okay, why? Okay.
The values go to minus one.
No, there is no minus in between 0 and 1.
You can put minus one, minus two.
But minus 1 comes there in the line.
No,
There's no between 0 to 1. There is like the complete number. Like,
No, like we can put it in decimal as well. So if I say that 0 0.1, 0 0.2, 0 0.3 and 0.
but it will finish at 1.
Yeah, it finishes at 1. So what do you think?
It's
You
not infinite.
understand or not?
yeah.
So do you think it's infinity or not?
No infinity because it finishes at 1. It's at 1 0.
Okay, what about if I say now like that 0 0.01, 0 0.02, 0 0.03?
Yeah, there is there.
So it will take it up till 1 will come.
Yeah.
But what about if I do it 0.00001?
Yeah, that's
Still it means it's infinite. So between 0 and 1, it depends upon how much zoom in I want to do. Okay, I'm zooming in to which number of scale. So if I keep increasing it, more numbers will come. So it's infinite between 0 and 1 as well. Make sense? Clear? Yeah. So so either you can say it's 0 to 1 or either you can say 0 to 100. Still in 0 to 100 infinite numbers possible because we are taking decimals as well.
There is some finishing point.
No, there is no finishing point. How? Because
100 is the finishing point.
no, it's a finishing point, but in between that,
Oh,
the number of possibilities are infinite. I can keep increasing one more zero, then it's again more. If I keep increasing one more zero, it's again more. So how I'll stop it? I can't stop it. Make sense? So that's why in analog, when we take our data, so in analog it means that in between that data it lies any in between somewhere, but we don't know what the exact value is. But with the digital, we know exact value. So in digital computers, store information in digital format. Text files, programs, songs, videos, all are stored in binary on associated digital media such as hard drives, USB drives, etc. So the main characteristics of digital information is that it is entirely made up of zeros and ones. So any bit of data is either a 1 or a 0, nothing in between. Okay, nothing in between, like this way, either it's 1 or 0. So then it's easy to translate into some information by computers, because when, let's say, I press a keyboard button, behind that there is some pulse of different bits generated in the form of zeros and ones, which sent to the computer motherboard processor, and it process it, and from there we are actually getting that information. Okay, so coming to the analog data, so our voice, we can actually record our voice and can see that's actually a analog data, and there is an infinite number of levels. For example, if I want to dissect my voice to see a very small sample of small, I can keep going on and making it as smaller as I can, if that software has the capability of doing that. Like for example, in some of the timers, they have till milliseconds calculations. You can keep increasing to nanoseconds, more femtoseconds or something like that. You can go there, you can do that. Okay, so the diagram below show analog voice data that was captured using a program called Audacity. So by this is a software from where you can capture your voice and can see how the data looks like. The second thing is to transmit analog data over digital networks, for instance, voice over IP, streaming audio, and other applications. The analog signal can be digitized into digital format and transmitted digitally. So we actually digitize it and then send it over the network. And for that, what we need is sampling rate. The higher the sampling rate, the better the quality. So before that, first of all, look into this image. What this image is telling us, why they are putting the images there of a building, human, butterfly, needle. What do you think? Why? Does it make sense? Hmm. Any idea how to read this image? Okay, just give you example. Let's say you have this remote, this length. I'm making it here like this length, let's say, and there are waves coming on like that, and then there is other type of wave which is more in fluctuation and more in number of times, and then there is other one. I just made three first. So which one has the more possibility to hit that target? The first one, second one, or third one?
The target means
Target is your that remote which is there.
everyone will hit the target because
No, no, but which one has the more
intensity.
probability, more chances?
That is the third one.
Third one. Why?
So it's making so many waves.
So many waves, or so many waves, and with the smaller value. It means that if the wavelength is smaller and smaller, it has more penetration power. So in our X-rays, when we do X-rays, and like with the radiation descent, they are very high frequency. Remember that when it is high frequency, then at the same time our wavelength is low. Okay, high frequency wavelength is more smaller, smaller, smaller. That's why when they do the X-rays, they can penetrate to our tissue levels to see that is there any fracture or not. So what they do is they send the radiation, they go back to the system. If they go whatsoever according to their study, that's okay. If there is some fracture at that fracture point, they will not send it back. It means there is a loop. They pass it. So that's how they know that, oh, this is having, some person has X-ray fracture problem. Similarly, you go to the airports when you have any metal thing in your pocket. If they are using a low frequency metal detector, then wavelength is so high that there is a chances that it passes here and there and that person skip that metal device. Whereas if it's a very high frequency device, it's impossible that that metal will be undetectable. Definitely, because wavelength is so small, it should pass it from there. Now coming to the point, so it says that when your wavelength is 10 power 3, so the frequency is only 10 hertz, 10 kilohertz. Okay, on 10 kilohertz we have a 10 power 3. So it means that at that stage the scale of a wavelength is a tall building as high as 1 kilometer high, tall buildings. So that can hit to that target. So it means that for a bigger objects we can use low frequency signals. But as we move to 10 power 8 and 10 power 12, we can see on a microwave, it's something like this way, only the butterfly width. Like in order to detect a butterfly in any area, we need microwaves. Bigger than that, going to this way or this way, it's hard to detect them. Whereas you can see items, X-rays, gamma rays at a very particular minute level, then we need gamma rays, which is very very small. You can see that their penetration power is, their fluctuation frequencies are higher and higher. Now it makes sense. Another way is one more thing in microwave oven, how your food is cooked. So if you realize that once you your the food particles size is bigger than the wavelength. Wavelength is much smaller than the food particle. That's why it goes inside, penetrate, and heat up this stuff. If it is using a very low frequency, maybe your food is not cooked. Okay. The last thing is about the sampling rate. Sampling rate. Sampling rate is that, as I mentioned, for any analog signal, so for any analog signal, let's say if this is an analog signal we have, and I want to reconstruct it because I want to make it a digital. Digital mean rather like I have a, because for every single point from here to here, for every in between, there are infinite number of values in between that. If I trying to uh, open it again, zoom in that, isn't it? 0 to 1 like this stuff. So if I want to do a digital signal, so what I do, I say, okay, I will make one sample here after every 2 seconds, maybe like this, something like this. So in this way, when I reconstruct it, I have only those dots. So I can do like this. Okay, something like this. But if I have less than those signals, one is here, one is here, one is here, then maybe it do like this way. So it means that more the sample values we are taken in, more it will be better to reconstruct the original signal. But if our sampling rate is less than some particular amount, I'm not going into that detail, but if it's less than that, then we are not able to reconstruct our signal back. Got it? So digital and analog transmission media, like data transmission media, is either digital or analog. Cable we use to connect computers was developed for the transmission of digital data. Devices like Wi-Fi access points, telephone system, microwave dishes are analog by nature, because once they are sending signals in the air, that's in the analog one. Because in the air we don't have a digital data. Once it is struck on the antenna, then it is converted into, by having some processing, converted into digital form. So what we use is using modulating analog transmission. Digital data can be sent over analog transmission media. So whenever the presence of one is presence of an analog signal could signify as a 1 bit, and if there is no signal, we say it's a 0 bit. So we are sending digital data over analog transmission lines in our systems. So if we're looking toward multi point to point and multi point circuits, okay, can you read that slide? Read it.
Point-to-point circuits are a direct connection between two devices. Such media is not shared with any other device. Multi-point circuits share the media with multiple devices. Ethernet systems that use hubs and Wi-Fi fall into this category because they share the media with other devices. In shared system, there needs to be protocols in place to ensure multiple devices can get access to the media.
Yeah. So what we are saying here is, now we can see from point to point is one which where two devices are directly connected to each other. Multi points are the one which are connecting with the multiple devices. So our Ethernet system, for example, our hubs, Wi-Fi, fall into that category where they are actually multiple points they are connecting with that, and they share the media with other devices. And then share system, there need to be protocols in place to ensure multiple devices can get access to the media. So share system where we have switches, we have routers connected to the systems, depend on that what from that share system information we need, but this is how they are connected with the media. Coming toward the data flow, there are simplex, half duplex, and full duplex systems. Systems can be categorized according to the way data flow between devices. So if we say the example of a simplex can only send in one direction. Something like, for example, radio station sending the data, we are only going to listen it. That's only in one direction. That's a simplex form of sending a data. Second is the half duplex system, which actually allows data in both directions, but at a time only one can send that information. For example, on a walkie-talkie.
Yeah.
Yeah.
On a walkie-talkie, one person will finish his talk,
And I
stop, and then other person will speak, and that's how they do the communication over a half duplex. Whereas full duplex is like the way our mobile phones are, and in that one they can actually uh, can transmit in both directions. Why it's possible? Because remember that whenever we are saying that, it means that we are making a channel, we are making a path. So the sending information to the other person having a different path, the receiving path is different. That's why we both are able to speak at the same time and listen and actually fight with each other. Whereas in this system, it's hard to fight with each other because one is speaking, other has to be stopped. So, so in this one, both can speak and maybe cut other person as well. But in this one, when one is talking, unless he will say stop or something, or maybe no one can hear to each other if they don't make a rule. So in full duplex, this is two channels. One is uplink, another is downlink. In incoming and outgoing. So on our phone, when we make a call, for our downlink channel is different, uplink channel is different. Then we have a concept of a multiplexing. Multiplexing. Okay, can you read this slide?
Multiplexing is used to divide our communication channels so the channel can transmit multiple conversations at one time. Some multiplexing methods are TDM, time division multiplexing, FDM, frequency division multiplexing, WDM, wavelength division multiplexing. In the time division multiplexing, different stations get to the transmit at different times. Station 1 gets the first time slot, station 2 the second time slot. A significant bandwidth can be wasted with the TDM. A variation called statistical TDM can allocate more access to the device that require it. This reduces wasted channel bandwidth.
Okay. So the main job of multiplexing is to actually divide a channel in a way that more people can do a conversation in one time. So, for example, there is multiple ways we can explain that thing. Before going into that detail, I just want to explain you something, the difference between time domain and frequency domain. So, if you get that idea, then it's very easy to understand. Okay, look to this example. So, in this example, you can see that, remember that this is your time waves going on, this one. This line, which is the first line, is there, second line is there, this is a frequency. Okay, this is the amplitude of the wave. How much is the amplitude? Now, before that, let's see if I show you this pen in front of you. What if you don't have a knowledge? This is a pen, or this is a marker, board marker. So how it looks like from here only? What you can see? Just a line. Just a line. A person, huh? Yeah, for your dimension. But the person who is standing there, he can see only a circle. He can only see a circle. So this is something like that. One view is from this way, and another view is from this way. So if you're looking from here, let's first take the time domain. I'm looking from here. This is a wave I have make it. Okay. So let's say this is a wave with the starting from here 1 and here it is finishing. So this is a frequency of 1 and amplitude, let's say 2. Okay, but and okay, this is first one, and the second one I made it because remember that this is a time signal, so I am actually making it multiple waves at the same time. So another wave, if I want to make it, that should be started at the same time at 0, but I make it a little bit at a different value. What that value could be get? For example, now start from here 1, 2. Let's say I say the frequency of this one is 2. The frequency of this one is 1, and amplitude of this one is, let's say, 1. Okay, so it means that this is at a position of 2. Frequency is amplitude is 2. Yes, frequency is 1 here. Here frequency is 2. So as you move forward in frequency domain, f because your frequency is going higher and higher, you're going far away from there and there. But it always starts from where? 0. Because all signals are starting at the same point. Now, when you see those signals here, you can see that this bigger one is the one which is with the amplitude 2, and the smaller one is the one which is having this is amplitude 2, this is amplitude 1. Whereas this red one has a frequency 1 and this is frequency 2. Okay? Now come to this point. See from here. Frequency domain. You can see only the pulses. This pulse is what value 2? This is amplitude. Because this pulse, why it's pulse? Because this whole information from here is only a line. Because we can see a line only. And therefore, we can say this is at value f is equal to 1.
This will be at 1.
Yeah, we can see f is 1 is equal to 2. At f equal to 2 is equal to 1. We can see that this one is this one. Make sense?
Yeah.
So now if you understand that thing, because this is how the two-dimensional things works, we can quickly have a look some examples. So you can see this one.
Same one.
This is a similar thing, but a little bit you can see how it looks like in different domains. So it is easy for you now to understand. If I want to, this is a time domain signal and I want to see what is the frequency of this one, I can see from their values this should be higher frequency than this one. That's why it is more on away from the 0 value. This is more near to 0 value.
Yeah.
And here this value, these two values are, it means that there is two frequency components in this time domain. This itself is a complete study, how to process frequency domain signals and time domain signals, and it's a very interesting thing you can see from here. And similarly you can see anywhere. So in the frequency domain and time domain, totally opposite to each other. Okay, now coming back to our multiplexing things. So here if you can see now, with the time division multiplexing access, let's say there are 8 students in the class and everyone students want to talk with me, and I said okay, one student can talk 5 minutes. Rather, like the 8th student has to wait for 35 minutes, because 8 times 7 56, sorry 8 times 5 is 40 total. 8 times 8 is 8 times 5 is 40, so 8 times 35. Okay, 7, yes, 7 times 5 is 35. So 35 minutes of talking, and that student has to wait for that much time. I said okay, rather we should like make it 1 minute each, then other person will wait in a queue, again come back, and in that way every student can get a time very quickly, rather waiting for that 35 minutes initially. This is the same thing happening in your field of like when we make a phone calls. our calls are also time division multiple plus XX as well, where when we are calling, our time in microseconds is given to us between the users, and it keeps switching, so everyone can get access. Otherwise, the person who, if the whole channel, the whole road is given to one person, so it's something, it's a something like that. This is a road going on, and if you ask that, okay, user 1 first for 5 minutes, user 2 5 minutes, then the person who is coming at the 8th position has to wait for a longer time. But whereas if we make it for a 1 minute, just give example, but in the field of telecommunication, it's in more than less than a microseconds. We are switching it between the users. So when it is switching between the users in microseconds, our ear can't differentiate that my call is switched between in turns. We are getting the call seamlessly, like without any unnoticeably, like there is a gap in between. Make sense? So this is a road, let's say. So, but the problem of this type of method is that once one is using, the whole channel is used, and that is a concept which is used in the time division multiplying XX. So what we are saying is significant bandwidth is wasted. Why? Because if user 1 is using for that 1 minute as well, still he's using a lot of that, whole road is occupied. Maybe he doesn't need that much. So another way to see that thing is, I can make multiple lines here, 8 lines, 8 rows, let's say, and 8 at the same time, with that bandwidth, with that road divided into 8 parts, 8 people can actually go at the same time. That is known as a FDM, frequency division multiple access. So what we are doing here is dividing the whole thing into more smaller parts in frequency domain, so our that bandwidth is not wasted. Okay, make sense? So, but on the other hand, with the time division multiple access, close it. Can you close the door? So on the other hand, with the time division multiple access, that method is also used on some time. For example, we know that there is a traffic at from 8 to 9 in the morning and then 3 to 4 p.m. So maybe at that time, by having a statistical data, we can use TDM, because we know that one person is using too much time, or no more people number of there, so we can allocate more number of people in TDM to do that thing. But every different multiplexing technique has different benefits. So in that way, we can reduce the channel bandwidth. Remember that your bandwidth is something like, for example, Telstra, Vodafone, other companies, Optus, they actually apply to the government to access a particular bandwidth. So, for example, for Vodafone, they have their allocation of a bandwidth, let's say 890 megahertz to 895. Maybe they were allocated 5 megahertz band only. So by having that, so they can only transmit and use that band only to give to their customers. For that, they charge for that. So it's a very bandwidth is a very particular thing which is not very abundant in value. We have a very limited one. So that's why we always use different type of techniques to reutilize our bandwidth. So this is what I explained. So different channels transmit on a different frequency. So AM radio is a good example of FDM. We know that, guys, please. So in AM radios is a good example, because we know that every radio station has their particular frequency where they are working. FDM was also used in the old analog systems, so that multiple voice conversation can be sent over a single telephone wire. Third one is a wave division multiplexes. In that one, actually more like it's use the fiber optics cable. Instead of one light beam being transmitted down the fiber, multicolor lines of different wavelengths can be sent at the same time, each carrying different data. We will see this one in few moments when we discuss about the optical fiber. Okay, can you read this one?
This one?
Yeah.
Digital transmissions occur between a sender and a receiver. This could be, for instance, two network cards on an Ethernet network. To ensure the receiver understands the data sent from the sender, the Ethernet protocol mandates voltage level, cable length, how the receiver identifies the start and the end of transmission, and many other properties. The ending of the data bits is one such property. Ending can be described as the way in which binary 0 bits and binary 1 bits are represented on the network media. Ethernet uses an encoding method called Manchester encoding. This method is self-clocking and so has advantage over some other many methods.
Yeah, so actually in digital transmission of data, again it's always happening between the sender and the receiver. So for example, our this network interface card from where our signals travel on the Ethernet network. So when we are sending that data, there are some Ethernet protocols which are really important, which include the level of the voltage, the cable length, how the receiver knows that when the data is being sent, when is the start of the data, when is the end of the data. These all other properties are important to see when the data is transmitting over a transmission media. And also there is encoding of data bits as well, like what are the data is encoded in some type of like we know that, for example, if I say that A is equal to 1, B is equal to 2, C is equal to 3. So if I say, okay, what is D, E, F, you can easily know that this is 4, this is 5 and 6. That's a simple example, but in that one we are using a Manchester coding, which we'll see later on today, how that encoding methods are used in the transmission media. And there are some advantages as well. And then the last point is self-clocking. Please remember that whenever there is a data sent between the sender and receiver, the clock should be at a synchronized. If it's not synchronized, maybe the clock of the receiver is already at 9:54, whereas the sender is on 9:53. He sent the data at 9:53, but the receiver already passed the time of 9:54. So for him, that data is already gone. So the clock of those two devices should be on the same point. So what they do, first they check it, they are self-clocked properly, then they are actually synchronized. That's why you can see our all online mobile devices, they have same time, because and that's why they are quite synchronized due to that reason. Now, how Manchester encoding works. So what happened in that one is that rather we are saying that when we start with 1, we say it's 1. In the middle of the value, Manchester coding is telling you that change it at that point. In that way, every time when something is going to change the clock, we can easily know that what's going on. So what we are saying is whenever the transition is doing on, it is in the middle of the bit, middle of a bit period. A positive transition is happening, it means a binary 1. If a negative transition is happening, it means it's a binary 0. Because there is always a transition in the middle of each bit, the sender and receiver have no problem staying in synchronization. So they can synchronize with each other due to, because they are in the middle of the bit, they are changing it. So you can see that, for example, this is your clock signal, because clock signal always say 10 10 10 10 like that. But this is your data 101001100. So we're looking at these two things now. Okay, here I will show you a small video because it's easy to see with the when we make the circles and graphs. See this one. This is your data 0100110001. It makes more sense for you to get understanding. So see, for a 0, we know that transition is negative and halfway. Then for the 1 we will make it like that. Just remember that for 0 always start with the high to low, and from 1, but it is, remember that we can see that it is starting from middle point, it is going up. That's very important to understand. From the middle point it is going up, whereas for this is at the middle point, we are at the low point. And we know, because it's, of course, when we are starting from the starting point, it's a bit tricky, because wherever we have to start, then from that point we take it as a 0. Let's see another one at the end, you will understand. So once we move forward and we know that it's 0 again, so 0 again means that in the middle of the bit we will change to next signal. So this is how it looks like. So this is how we make it. This is 0. Make sense?
Yeah.
Then this is 1. Is it clear? If you have a pencil, try to do it, because it looks very easy here, but if I say to draw by yourself, you will not do it. You can't do it until you have a practice of 2 to 3 times. Okay, so next, again 0. So see, with the 0 it is going halfway up, then 0. Okay, let me know what we should do here now. It's 0. Hmm?
No, we start from 1.
See, remember, that's important point. When 2 zeros come, because there is nothing transition happen, so it will start from again. So that's how know that clock is synchronized by the sender and receiver. Make sense? Because this is a tricky point here. Maybe you have a question in your midterm test as well. That's why it's important for you to understand. So now we can see, we make it like that. It's 0. So remember that whenever 2 of the same bits comes, then you need to redraw by yourself. You don't need to rely on the past values. Like the way when 2 zeros come, we just stop it there and then make it 0 again. Yes. So you can see that now 1 comes, positive transition, stop here. Then from the beginning, from the bottom, because 1 is always positive transition. Then 0, stop, and at the end you can draw, make them touch to each other, because you can draw them. That's not a problem. Because if you do it while doing it, you will be confused. You will be confused, because you will, these lines you can make it later on when you finish it, because otherwise if you do it at that time, you will be mixed up. Now 0, again it start from top to bottom, because 0 is top to bottom, and then you can draw it. Then top to bottom, and from now 1 comes from the bottom to up, and then again bottom to up. So this is how the Manchester coding looks like. Make sense?
Yeah.
Now you can see in your one, because don't worry about this clock signal, see only these two. So 1 going up, going 0, going up, down. So here again, so again start from 0, because yesterday in class when I was explaining to the student, I didn't have that video which I showed you. So they were really struggling to get the answer. So I thought I need to change my method to your class. So now you understand from that video, which makes sense to you, why it's like that. So then again from 0 to 1, going up, and then from here to here again 0 to 1, 0 to 1, and then you can do that. Clear?
Yeah.
Okay. So positive transition is a binary 1, and negative transition is a binary 0. The signal is positive half the time and negative the other half. So no net DC component. DC component means no value on 0 value on original this value. See, if we start from here, but nothing in between there is any value on that, due to that half time variation in positive and negative. Now coming toward the transmission media. There are many types of transmission media used in network and communication system, including, like, there are different type of transmission media, starting from unshielded twisted pair, coaxial cable, optical fiber, terrestrial microwave, and satellite microwave and infrared. These are 7 to 8 different ways where we are used in our telecommunication network to send the data. It depends. That data is sent between the one person to another person, between one person to the shared network, one person to the different devices, or between countries to countries, between cities to cities, between different networks to networks. Some data are in the form of a small amount, some data in the amount of a huge chunk of data, based on that. So if we start from twisted pair, okay, can you read that? Twisted pair? Yeah.
Consists of two insulated copper wires arranged in a regular spiral pattern separately insulated. A pair of wires act as a single communication link. Wires can be sided STP or on-sided UTP. All twisted pair can span a distance of 100 meters, and after that it needs devices to amplify signals.
Yeah, so there are two twisted pairs. They are insulated with each other, and there are some are in shielded one, some are unshielded one. Unshielded are UTP and shielded are STP. And usually their overall distance cover up to the point is 100 meters. And after that, you need to amplify or boost the signal again if you want to send it again. So once we finish those all transmission media things, you will know that, okay, at which type of things you are going to use which type of transmission media. So here we can see there are 7 different categories of twisted pair based on their applications. Usually category 1 are used for telecommunication, telephone lines only, not suitable for transmitting data. They are only for voice. They are more used in the olden times phones. Category 2 are actually can handle data as well, up to 4 megabits per second with the voice, of course. Category 3 are actually 10 base T networks, we name it, and they can up till go to 10 megabits. Category 4 is actually using the token ring, and they are actually speed up to 16 megabits. So you can see that, of course, this technological evolution was happening from last 40-50 years. So starting from category 1, and people start working on those things, and every 5-4 years new advancement comes. And if you remember the time of 7-8 years back, our YouTube videos, we can't run it on our mobile phones because there is no concept of HDMI. There is no concept of synchronization of videos, because the videos sometimes takes maybe half an hour to stream it. Then you are able to use it. So category 5 actually is consists of 4 twisted pairs, means 16 times 4, 64 megabits. Whereas category 6 has the capability of sending back and forth both ways, capability to backward compatibility as well to send the data. And category 7 is very much near to category 6, but more accurate, more stringent values are needed on that. Okay, looking toward the unshielded versus shielded. So unshielded, used in telephone system, token ring networking, and used for networking. There we know that, as we have seen in the last slide, Cat 5, 6, and 7 are more like a high data rate speed ones used for networking. And UTP does suffer from external electromagnetic interferences. So like when in the older phones, someone is talking to you and there's some other person's voice is coming in between. That is known as a crosstalk, and it happens sometime due to the issue of your the signals, your data which is going on the those twisted pair lines are actually mixed up with the other channel signals, and in that way you can hear their voice. And that is actually that electromagnetic, because remember that whenever any wire has a current going on, there is electromagnetic waves around going on. Due to that, it actually takes that data to that thing. For example, when we tap a card, again EM signals are generated at that time. So with the shielded twisted pair, the so basically in order to focus on this problem, how to minimize that external EM interference, we are using STP. That's metal braid or sheathing that reduces interferences, higher data rate, and more expensive. So the metal braided is the some extra coating on that, which is on the outside to make it more safer and less problem with the interferences things, and harder to handle because it's a bit thick and heavy. So, but again, it depends what type of services you're using. Based on that, you're going to use it. So there are overall, if we see the twisted pair, they have a lot of different benefits and demerits. Depends on their usage. They are not expensive, easy to work with, low data rate, short range, but higher attenuation. Attenuation is a function of distance. So means when any data which is traveling over a network, after a certain time, their amplitude becomes lower and lower and lower, and they are become weak. So that's known as the attenuation. Coaxial cable. So coaxial cable consists of two conductors. So this is another way of transmission media, inner and outer. Outer conductor is braided shield. You can see that. Inner conductor is solid metal, separated by insulating material, and usually their diameter is 1 to 2.5 centimeters. So you can see that this is outer conductor, inner conductor, and this is outer sheath on that. If I show you the coaxial cable here quickly, so here you can see this is how it looks like. So you can see this is a inside copper wire, this is a copper mesh insulation, and then outside insulation. So this is a coaxial cable looks like on that. And there are more, or this is another way to, you can see that these are all coaxial cables. So they have two conductors again in the circle form. So it is expensive and resistant to electromagnetic interferences. This type of coaxial cable are named in two different forms: thin net and thick net. Thin net is having a distance of 185 meters and provide 10 megabits, whereas thick net can range up till 500 meters. So it means that whenever you are using coaxial cable with different characteristics, they have their capacity to throw the data away in the wires as well. After that, you need a repeater or a booster to make it more faster again to re-energize the signal again. So there are two common types of coaxial cable: baseband technology and broadband. In the baseband, it is actually using the entire channel for its transmission. So at a time, only one signal can travel at a time in one direction, because you are using that whole frequency bandwidth of that. Whereas in broadband, you are dividing the whole bandwidth into smaller parts so that multiple type of data can be transmitted at the same time in both directions. So that's a broadband technology. So that is the difference between these two both. So if we see the coaxial cable, what are their characteristics? They are much more better than twisted pair, but performance is limited by attenuation noise. Analog signals requires amplifiers every few kilometers or closer if carrying higher frequencies. For high frequencies, of course, when you're going on high frequencies in coaxial cable, then there is more attenuation. For digital signals, repeater every after 1 kilometer or closer for higher data rates. So coaxial cables were common in early type of Ethernet system like in a 10 base 2 and 10 base 5. We know that for 10 base 2 thicknets, which is 185 meters, at thicknets which are for 500 meters. So we used for those digital signals and analog signals. Now coming toward the optical fiber. So that's another way of other thing which is used for communication. So okay, can you read that?
Optical fiber. Where optic cable box is a physical medium that is capable of conducting, modulate, modulate light and spectrum. It carries data over glass over light waves, glass or plastic code.
Close. Excuse me. Close the door. Yeah, please close the door if you go outside. Okay, that's fine.
The glass core is surrounded by a protective casing which is enclosed inside an outer jacket. It has a higher transmission speed that allows signals to travel over a longer distance. All fiber optic can expand a distance more than 2 kilometers, and after that, it needs a device to amplify signal. Laser or light emitted direct. Especially design jacket.
Yeah. So optical fiber up till now, with the recent technological stuff, it has the maximum bandwidth our transmission media to take it. So if we go and just want to show you the optical fiber, how it looks like and how their construction is, and what are the main important things in that. So here you can see that they have mainly the core. This is a fiber like a glass. Then there is a coating, cladding, and then there is an outer jacket. Mainly three things: core, cladding, and outer jacket. Something is used more for to make it more strengthened. So remember that it's a glass like a fiber, very thin, very thin. You can see those lines or like this, and that one the if I make, where is the pen? Yeah. So if you see that this is a glass, so it travels very faster like a speed of light, and with we know that for the rainbow they have 7 colors. So when colors are different, they have different wavelengths. So WDM, which we have seen, wavelength division multiplex access. So with different wavelength, we can send different data on it. So this is how this technology is used. So here we can see that core, cladding, and jacket, and you can see this is light at less than critical angle is absorbed in jacket, but if it's proper, then it is keep sending that data. So in the optical fiber, we have single mode or a multi mode. In a single mode has a small glass core, can transfer data over a long distance, and is less susceptible to attenuation. Like there is less, it is there is a it don't attract attenuation. It is quite immunized to attenuation. Multi-mode has a large glass core, can transfer more data but only up to a shorter distance. So again depends on the usage, where what we are doing is single mode or multi mode, depend upon the usage. But again remember that the angle of reflection is the one which is more than a critical angle to work it on. So it has a very much higher capacity than the all other type of transmission media. It can send over gigabits of data over 10 of kilometers. Lighter than UTP cable, considerable advantage in laying, lower attenuation, electromagnetic isolation is very good in that, and greater repeater spacing, like tens of kilometers at least, then you need to repeat it. That's why they are more used in the back-end networking, LAN switches, long haul trunks. Long haul means, or a backhaul means, which is on the networks of a cities to city networks to connect, to country. So, or a network where the whole, let's say on a normal network, thousands of people are communicating to each other, but on the back end, those data need to transform from one device to another area or from one area to another area. So you need big pipes, let's say. So for that, optical fiber is the main thing which helps us. Metropolitan trunks, rural exchange trunks, subscriber loops, NBN, which is right now we can see that in Australia, most of the houses they have installed the optical fiber already on that. So if we see the characteristics, as I mentioned, they are using total internal reflection to transmit light, which actually can act as a waveguide, because as I mentioned, this is like a wave moving on in the uh, glass as a guide. So waveguide up till how much? 10 power 14 to 10 power 15 hertz. It's a very huge, like more than terahertz. And what they are using, the light sources are LEDs or ILD. So these are the lights. By that, on that one, our data is transmitted. So that's a very, I would say, that one of the main innovation of the recent 10-20 years, where a lot of work has been done on that, and due to that we are enjoying the high data rates. So with the transmission mode, they have three different modes. Basically, if you see that step index multi-mode, they have different type of waves, how it is going on, with graded index multi-mode and then single mode. So these are the different type of transmission modes are possible in optical fiber. Here you can see their characteristics. For local area network, we are using you can see that it is in terahertz. So again, remember that when we are talking about this thing, so one thing is important. For example, this is in terahertz and this is in nanometers. So small wavelengths. So if you want to find out how to find the lambda value, the value of the C is equal to f lambda, and lambda is equal to C over f. So you can find it out if you put this in 366 3 times, and the value of C is 3 times 10 power 8 meter per second divided by 366 terahertz. Tera is equal to 10 power 12, I think. So in that way you can find out that value of those things. So, and this is a multi-mode, which is a local area network for a single mode, various devices for wavelength division, multiple access at different band labels. You are using those ones at for those optical fiber. So you can see that they are using very higher frequencies, and that's why their transmission rate is very high. Then we are coming toward the terrestrial microwave. What is that? Terrestrial microwave. Terrestrial means in the space, which is, for example, you are in the companies like Vodafone, Telstra. If they have to deploy a network in the rural areas or hilly areas where there is no possibility of putting wires, what they do is they they actually add the um, terrestrial microwave links to make a point-to-point connection. I will show you how it looks like actually, so you have the idea of that thing in your mind. Terrestrial microwave. So, for example, usually they are this type of dishes, something like this type of dish. You can see this like the circular form. These are the dishes which are these are all for microwave links. Those microwave links are always on a line of sight to each other. They can see each other. If on a one hilly area you put a tower, on that one you are putting this one with their height. You need to adjust another one where you are putting 2 kilometer away or 1 kilometer away. So with that microwave link, you are sending huge amount of data to that area, and then from there you are moving forward that data. So again, it's you can see that this is a line of sight where they can see each other. So remember that these are all line of sight terrestrial microwave links. But whenever you see the ones with the this one, so you can know from now onward. For example, if you see these type of things, these are used in more for sending the signals to us, to our mobile phones.
Yeah.
For mobile tower with this one. But if there is something like this, they are for backhaul communication. To, for example, our 10,000 customers data already reach there, but they want to send through that all 10,000 customer data to the next level because they don't have wires to send it. So then we use those dishes. They have microwave links with a very high capacity to send through a wireless link. Okay, and on some of them are having those, you can see, with the users as well, and for the microwave links as well. But in the city areas, you never see those type of dishes. These ones. If there is this one, that means that wherever there is focusing in it, you will see another one somewhere else where you can see each other. because to make a link, because in the cities they don't need it because there is already underlying network of optical fiber is there, so they don't need to make it in that. That's more in the hilly areas or on the motorways or in the rural areas where you don't have enough facilities to do that. So we use a parabolic dish to focus on a narrow beam onto a receiver antenna. That's a parabolic dish which I showed you in the form of a drum. It uses 1 to 40 gigahertz frequencies, and the main source of loss at this level is a distance and a rainfall. If the distance is too much, then again those microwave links signals are less. And rainfall has a droplets of a size of microwave links. So if it is a size of that, so whenever rain happens, due to that your signal deteriorates. That's why whenever the rainy weather is there, in the hilly areas especially, you can see there is a outage or something is not properly working, and also they can suffer from interferences as well. Then coming towards the satellite, that's another way of transmission media. Again, in that one, when you are in the area where there is no such ability to have anything on that, but if you have a satellite phone, then you can straight away connect to the satellite and you are able to communicate and can send your data through it. So satellite acts as a relay station. Relay station means take your data and just give to someone else on the other side. So they have their uplink frequencies and downlink frequencies. So for uplink is different and downlink is different. So for example, again, just to show you a satellite communication stuff quickly. So here you can see that on one part of the earth, this is uplink going to satellite, and now downlink on the other one, and these are ground stations. So they can at a height of 35,784 kilometers and space at least 3 to 4 degrees apart from each other, those satellites. So for example, our televisions, long distance telephone, private networks, global positioning system, they are all work on a satellite. So the one satellite earth station is there. This is a point to point link where this whatsoever, because the earth curvature is changing after every 21 kilometers. After 21 kilometers, it just tilted a little bit. So if it's tilted more than that, then the antenna which is here can't see here. So it's mean terrestrial can't work, optical fiber is not there. So then satellite is there to help us. Whereas on the other hand, if there is a cricket match or there is a live match going on somewhere, from there you are transmitting the signals to the satellite. From the satellite, you are getting that signal to all other multiple receivers in the world, wherever you want it, based on their uplink and downlink frequencies are already fixed for that. The last one, infrared. Infrared, where we use it? Anyone idea?
Or infrared, there is the infrared sensor
What happened?
in mobile phones.
Mhm.
The infrared sensor, we can see in our eyes and as well.
Remote controls.
Yeah.
Remote controls have infrared lights. Okay. So that's a very end line of sight or reflection are blocked by walls. If a wall is there, our remote can't work. No license is required. Typical user IRD reports or TV remote controls. They are also sending a data. So remember that whatsoever the today's lecture was about physical layer. So physical layer includes your twisted pair, coaxial cable, your optical fiber, your that's terrestrial microwave links, satellite links, infrared. So these are the all different methods from where your data can be sent. That's all for our today's lecture, and there are some more characteristics of various medias you can see online as well on this link. And next topic we'll see is next week is cloud and mobile networking. Any questions before we finish? Because you have the now midterm test which you need to do that. No, like you have time from this today till 13th.
What's the syllabus?
You can from week 1 to 7.
1 to 7.
Okay, you can close that one. Yeah, week to 7, 1 to 7.